Hello, my name is Ian Howard, and today I'm going to talk about studying robotics at the University of Plymouth. So first of all, what exactly do we mean by a robot? Well, obviously in the movies, robots have been portrayed in certain ways. For example, Robbie the Robot, which is a kind of a useful robot that can do lots of tasks that stop people needing to do them. But there's other films as well, and more recently we have the more sophisticated robots like Data from Star Trek, which is effectively almost human in appearance and ability. But of course this is stepping a bit into the future, although maybe not as far into the future as we think at the moment, but certainly we've got a way to go. But in the real world we do have real robots out there working hard day and night. One example would be would be a standard sort of assembly robot kind of design. These are sort of very big, powerful machines that can be used to do repetitive tasks, moving things around, also assembling components as well. Another example that these big industrial robots can perform are things like welding. They're very good at actually welding pieces of metal together repetitively, and they're used extensively in production lines of cars, for example. Now, one issue with this kind of robot, it's a very, very big, powerful robot, so obviously you can't go anywhere near them as a person because they are actually very dangerous to be around. It's a big piece of metal moving at high speed, so you would normally have these things put away in cages to keep people out. There's other applications of robots which aren't just doing assembly work or construction work. For example, moving stuff around in warehouses. So, if you buy something now online, the chances are, if it's from a big supplier, they'll have robotic assistants which basically can pick stuff up, pick up trays and move them around the warehouse to the suitable location so they can dispatch the stuff for you. And this is an example, in fact, of an autonomous robot, which is effectively like a robot vehicle. But in a warehouse, it's a very structured environment because it can all be laid out to suit the robot as much as possible and make life easy. Another example of this kind of technology, which is then extended to an unstructured environment, would be an autonomous vehicle. So an autonomous vehicle is also a kind of robotic device. It's able to drive, it's able to move around. It's got sensors on it, for example, a laser rangefinder, so it can work out where it is in the world and in the road. And it'll have a computer control system in there, so it can actually navigate and calculate what commands to give to its actuators so it can drive where it's supposed to be going. Now, all of these things that we've been talking about, building robots to do manipulation, building autonomous vehicles, they're all things that rely on sensing things and actually actuating things, and these are things that you're going to be learning on the robotics courses in Plymouth. A bit closer to home than these big machines and autonomous cars, you've probably also come across things like robotic vacuum cleaners. And this is another example, really, of a mobile robot. And they're actually quite sophisticated now. I don't know if you've ever tried them. I got one recently and it works amazingly well. I'm quite impressed. This particular one I'm showing you here at the top is actually got a laser rangefinder on it. So what this thing can do is it can scan the room it's in, build up a map, and then only visit places it hasn't visited already to suck away all the dirt. So if you haven't got one, I recommend you get one as fast as possible. Another kind of autonomous system, which unlike something like a car, actually flies through the air, is a drone. And this is a kind of little tiny helicopter, or it could be a quadcopter, it could have even more propellers on it. But again, this is using the similar kind of technology as automatic cars. In this case, it's also got a balance as well, so it's got other sensors to make sure it's actually flying at the right orientation to the ground, but it can also sense where it is, and it can do things that are useful. For example, drones are very useful for actually moving cameras around and surveying areas, or in this particular case, as you can see, this is actually some agricultural drone that's actually shooting some pesticide down onto this field. Another big application area, or some which is becoming bigger and bigger, is actually using robotic systems to do surgery. Now, they're not autonomous. It's not doing it on people on its own under complete computer control. What you have with this kind of system is you're having some surgeon, probably close by, but it could be a long way away, who's operating this thing, if you like, remotely. So this is good because these systems, first of all, can actually be made to be more precise than humans are. We can, you can scale things down, so you can actually get very, very stable movements from these kind of things. They can operate through little tiny, pinhole surgery, I suppose they call it. But also the other thing is, you don't necessarily need the skilled surgeon to be at that location in order to run these things. So if there's an important operation that needs some expertise to run, using a link across the internet, you could have someone running this kind of system, in one city and actually operating on someone in another city. Again, a great application of robotic technology. So, what about studying robotics in Plymouth? Well, we offer 2 undergraduate courses. We have the BEng course, and this will last 3 years, so it's 3 years of study in Plymouth. Or you can do an additional year, bringing it up to 4 to get the MEng qualification. In both cases, you can do an optional placement year, normally between the 2nd and the 3rd years, where you go off to industry, and I'll say a bit more about that later on. In Plymouth, whether or not you study robotics or electronic engineering, the first degree is the same anyway. So this gives you actually the opportunity to decide really what do you want to do. Would you rather do electronic engineering or would you rather do robotics? And it doesn't matter really to start with what you go in with. You have the first year, if you like, to decide what you want to do. So here's a picture, a video should I say, of the Smeaton Robotics Laboratory done by one of our technicians, Jake. And this is really where a lot of the practical and experimental work will actually take place. You'll be in the laboratory learning things from a practical perspective. And here's, for example, an example of a demo of student projects that they've done for a particular module. They come into this area. They can also, they can come in. You can come in, if you like, out of hours to carry on and do your work. Very useful resource for students to use. We're very fortunate that we've got very good technicians which assist, first of all, provide technical support for the lecturers during teaching, but also very much so for the students as well. So we have a great team of highly qualified technicians to help you when you come to Plymouth. We've also got a lot of facilities for students and student projects and student modules. So apart from the technical support that you actually get, we've got all of these laboratories which are actually available for students. So I think that's a big bonus. You can come in, do your projects, carry on, almost use it like a common area. And then there's facilities that are available within this building. You can then use laser cutters to cut things up for certain construction projects. And we have some 3D printers so you can actually build custom parts for your designs. The robotics course and the electronics course in Plymouth both share the first year very much so. And so we've got common modules. I shan't say too much about it. I'll leave that to the electronics guys to explain. We start off, obviously you start off needing to know something about analog electronics, what are our, RCL components, inductors, resistance, capacitors and all this. How do they work? What are their characteristics? How can we build simple circuits with transistors? How can we use simple operational amplifiers, that kind of thing. And of course the world's very digital these days as well, so you need to know about digital electronics, logic gates and so on. And of course, increasingly, computers are playing a very, very big role. So we teach you about computers and microcontrollers and how to program them as well in these courses. Now, obviously, we can't just sort of guess about quantities or, as an engineer, we need to have a good scientific understanding of how things work. So we need to do mathematical modelling and calculations. So you'll get mathematics in the first and the second years to make sure that you can deal with that important side of the subjects. And of course, importantly as well, you get the opportunity to extend your knowledge of software and programming in a more advanced software program modules. We always have a third year project as well, which again really gives you the opportunity to do something you personally find very interesting. Obviously, most of the courses, you're doing a planned set of lectures that we've thought of are important for you and the IET think are important. In the third year project, it gives you the opportunity to say, right, I want to build this little robot or something, and I wanted to do this for a long time. In fact, we've had people come in. One guy actually built a Mars rover, would you believe? And it's something he said he wanted to do for a long time, and he did an absolutely fantastic job. So the third year project really lets you do something that you want to do and learn specifically on a particular topic. So let's just have a little now think about what is a robotic system. And we can think of this very basically, and I'm going to just think of it in terms of 4 parts. Obviously, you could divide that up a bit more. But basically, a robotic system is going to have some kind of mechanical structure, right? We've got to have, if it was an arm, you'd have links and bearings and all this. So we've got this mechanism, right, which is really what's going to do lots of the work. In order to get this thing to move, we need some kind of actuator. We need something to generate force to actually move this thing around. This is just an example of a stepper motor, which is a very cheap and effective way of generating rotary movement. Another thing we need to do in a robotic system is actually to measure what it's doing. Right? If we build an arm, we want to know what the angle of the arm is. How is it moving? How is it interacting with the world? So for this end, we need things like sensors. And here, for example, is an encoder which would measure angular position. Finally, of course, because we want things to do something useful and we want them to do what we want them to do, we need to put some kind of controller in, and typically this is operated using a computer. So, for example, here we're using a simple microcontroller to run an RC servo. We'll also care more about the mathematical details of this when I talk about control engineering. So, how do the modules for robotics teach you all of these interesting things? Well, we start off specifically in the first year with a sort of a kind of general overview of robotic systems, which also electronic engineers can take. And this introduces things like computer-aided design. So computer-aided design is a fantastic way to design things. In the old days, you used to do it with a piece of paper and a ruler. These days, everything has gone onto computer systems, so you can really design things using computer-aided design programs. We obviously want you to build stuff while you're here, so this course will also introduce you into designing and getting stuff cut with a laser cutter and 3D printing. And of course, electronics makes great use of printed circuit technology, so this is going to be your first introduction to doing that kind of construction and design. And you'll get a little mini project, so we throw you in straight away with doing some project work and do something practical. So, it's not all theoretical. You get something exciting to do that's building a little robot right from the very start of the course. In the second year, we need to teach you about sensors. How do you measure things going on, and how do you generate actuation? How do you get things to move around? So most actuators, right, like a motor or a stepper motor, they're basically magnetic devices. So we have to give you a bit of theory of magnetism. Then we're going to give you theory of sensors, and a good example is an incremental encoder. But Plymouth basically takes the view that the way to really learn something is actually to do it and to build it. So we have a lot of nice practicals for you to do to actually reinforce your understanding of this kind of subject. For example, we won't just give you the theory of an encoder. We'll say now we want you to build one. So here's a motor, here's a couple of components, an LED and a photodiode. When a slot goes past the photodiode, basically it lets the light through and you get a pulse. So you can build something which will actually, in this case, easily determine the rotational speed of a motor from first principles. Another little project to make sure you understand DC motors, we actually get you to build one from first principles. In the first case, it's just thrown together from, we give you some wire, we give you a cork, we give you a couple of magnets and a bit of wood, and say, right, off you go, get that working, get that rotating. And by the time you've actually sat down and done that, right, you'll already have a very good understanding of what the principles of these things are. And then the next part of this particular module is to get you to actually build a proper motor yourself, design it yourself, so you can think a bit more about it and understand the theory of motors much better than you would otherwise. And doing things, you're much less likely to forget what you've done, right? It's difficult things to sink in when you're just doing theory, but doing things practically really is, I think, a good way of reinforcing knowledge. Another course in the second year is something now I'm teaching, which is on robotic manipulators. So this is a little tiny arm, and we use as an example 6 degrees of freedom, right? So it's got 6 joints. And in order to understand what to do with these things, what we have to do is, first of all, we have to say, well, here's the arm. We can set the angles of its joints with its little motors, but what we care about is where the end point is relative to the base, right? So where's the end point of this thing? And it's affected by where the angles at the joints. And actually the relationship between what the angles at the joints are and the end point comes under the umbrella of what we call forward kinematics, right? So we know, if we know what the angles are, we can work out the end point. The other way round is saying we want to get to a certain endpoint and we want to work out what the angles are, and that's called inverse kinematics. So this is sort of very fundamental to learning to use robotic manipulation, and those things are very much discussed within this module. We're also caring about things like the force relationship. How hard does it have to push at a joint in order to push so hard at the end point, and how fast is it moving at the end point given it's moving a certain angular speed at the joints? And that's basically the study of force and velocity relationships. In this particular module, like I said, you get the chance to model, analyze a 6 degree of freedom arm like this, and then we have some of these models, these arms you can actually use and in the real world, so you can actually get something to really move around for the first time. Another module I teach is control engineering, and the basic idea of control is we want to get things to do what we want them to do. So one thing would be, like, for example, imagine trying to balance a pole on your hand. Normally this system would be unstable, so you'd have to move your hand around in order to actually achieve that. And we can sort of model that in a theoretical way using what we call is the pole cart problem. You've got to move the cart so the pole doesn't fall over. So we've got a nice practical we give you in order to do this. And this is what the video is showing at the moment. The cart's got to move backwards and forwards to keep the thing balanced. We can analyse these kind of systems in various ways. We will teach you about classical methods like Laplace transforms, but in addition, more advanced systems, analysis methods such as state space modelling, which is based on effectively linear algebra. And then, given your understanding of these systems that you'll pick up in the course, you can then build controllers to do all of these kind of tasks, to get things, for example, to balance pendulums, or to move an arm from one position to another with no overshoot, that kind of thing. And the coursework actually was to build the controller to actually control this pendulum. We also have a module in the third year which is on computer vision. So vision's used for various different things in robotics. It could be used for recognizing stuff, but the other thing it could be used for is telling where things are, right? You can see something so you can see its location. So this is a vision for control, a vision for tracking course. We want to know where things are by looking at them. And this course is inspired by animal vision, and then it moves on to saying how can we build artificial systems to actually do this. And we've got this nice basically practical that we run with you using what was called the Plymouth Owl which is developed by Phil Culverhouse and others, in order to actually get you to actually program a real system to look at the world and locate stuff. There's also a third year module which then extends looking at just arms to looking at mobile robots and actually humanoid robots. So this gets a bit more exciting. And again, we have to know where, where the limbs end up, given we know the angles of the limbs, and that's again basically extending our understanding of kinematics to these bigger systems. We care again about forces, so we have to think about the dynamics of this system as well. How do we get the thing to generate the right movement? So we have to model the motion. We have to integrate the head with the vision system into what the system's doing. And because this kind of system is becoming a bit more complicated, we need to think a bit more about the software organization. And for this particular model, you'll learn more about something called the Robot Operating System, or ROS, which is a nice way of managing complicated robot systems. And of course, you'll be doing simulations on this particular module as well. Another third year module that I teach, in fact, is machine learning. So what is machine learning? We really care about building systems which can learn from data in a nutshell. And they can learn to map continuous things to continuous things, or they could learn to classify. So classification, for example, would be like, imagine you've got images of handwritten numbers. You give an image to the classifier, it processes it, and it tells you what number is. One of the main focuses I have on this course is actually looking at artificial neural networks. So how can we train networks in order to do these regression and classification tasks? Another important part of machine learning is also concerned with learning actions, and this comes under the umbrella of reinforcement learning. So, for example, if you want to navigate through a maze, we can actually set that up as a reinforcement learning problem. You want to know which direction you should go in at any particular step in order to get to a target. In fact, the final practical for this actual module is building a simple learning algorithm which will find the best path through a maze, and then training a neural network to get actually a little arm to move through this space. So this is just an example of a poorly trained network which isn't doing very well, but you can see it's basically trying to, given that where it wants the endpoint to be, it works out what the angle should be, and it then can actually navigate through the maze. Moving on to the fourth year, so this is an MN module, we then can look a bit more detail in more complicated things. So looking, for example, at the science and technology of autonomous vehicles. Again, we have to then worry about, what's the relationship between, the angles of the wheels and where this thing is going to be. So again, we look into kinematics. We come across this topic called odometry, which is concerned of effectively working out where the thing is on the basis of sensors in the environment. Another thing it does on this particular module is look into what's called SLAM, which is concerned with localizing where a particular robot is at the same time as building a map of where it is in the real world. And of course, just like an autonomous car, it's not much use unless it's able to plan the route and actually control the thing so it gets from where it is now to where it's supposed to go. So we look into planning and motion control in this module as well. And because it could be that we have a system with more than one robot in it, or more than one autonomous vehicle, we have to think about multi-robot systems as well. How do we coordinate them as well together? Another MN module is going to be then on thinking about the more sophisticated software that we need, and how do we basically communicate between lots of systems which are not necessarily all in the same location, but also interact with the world and themselves. So this is going to involve, again, using sort of a mobile robotic platform, and you'll be concerned with low-level programming of this system, but also high-level programming as well. So it's a sort of a mixture between low microcontroller programming, but higher level programming to actually get more complicated behaviours out of this system. And again, because these systems start becoming quite complicated, we again will revert back to using control of these distributed systems using the robot operating system. So, of course, on the course, you have these modules and you have finally a project, but we also give you the opportunity to work in industry for a year, right? So if you really want to, and I would very much recommend that you do so, try to find somewhere that will take you as a placement student. And this really is very good for your perspective because it greatly increases your employability. Quite often, companies that people do placements with will take them back after they've done their degree if they so wish to do so. Another thing you really notice as a lecturer is students who've been out on placement come back and they're sort of kind of energized and they take their degree much more seriously, and they generally do much better than they would have done before because it's given them another insight in what the real world's like, and it makes them realize they want to do really well with their degree, and they generally do. So we've had some great locations for some of these placement students over the last few years. I'm just going to mention a couple that I've sort of been involved with a few of. One is like ARM, which is basically this fabulous producer of computer technology chips, based in Cambridge. That was a fantastic location to get a placement in with one of the students. In fact, we've had a couple go there. We've got this really big company in Plymouth, Babcock, so that's also a really good address to go to. I've had a couple of students going to Chess Dynamics, which is basically really into control and building systems to sense things like, for example, drones. And they're based in Plymouth, but also in Horsham. We've got Schneider, which is also it's actually French company that does a lot of automation work. And again, that's also based in Plymouth, but there's lots and lots of other opportunities out there. I'm just listing a few here that you can find. Like I said, it's really up to, again, students can, if they want, they can just write to as many companies as they like, choose the one they want to go to, and hopefully they get it. Also on the MEng, there is a project, which is, I think, quite often done as a group project. But this, again, it brings the opportunity to do something a bit more that you want to do and that you find exciting. We also have students who even manage to get some interesting work out just on the other modules. And this is a good example with Rebecca and Charles, who actually did a project on one of their modules, building this little spherical robot that rolls around, and it could be controlled over a connection to a wireless controller. This thing was 3D printed, and they submitted this to an undergrad a conference, the Taros conference, and got it accepted and got a presentation in there. So this was really great. So this is a really nice outcome for, I think, a module to actually get into a conference. Especially if you're interested in more in research, it gives you an insight also of what's going on in robotics in the country. You can talk to other people working in the field. That was really a great conference to go to. So I think it's fair to say that most lecturers or associate professors at universities are very much interested in research. Certainly that's true of me. And we are generally very research active in the department. And this is really good. We do have good recognition for the work, but the really good thing about it from the teaching perspective is it feeds into teaching, since we're very up to date with what we do, we're very excited by what we do, and this can really feed into the teaching in a very positive way. So my research, for example, is, I'd say, human motor neuroscience, understanding how the brain works in terms of understanding how the brain controls how we move. How can we run experiments with people and find things out about the way the brain is controlling things. That then we can then model computationally, and then feed this information also back into understanding how to build better robots. But at the same time, having a knowledge of robotics is also a nice insight into the way people work. So I think there's a two-way interaction between understanding how biological systems like humans work and understanding how machines work as well, and they, both viewpoints interact and help you understand the other. Dr. Mario Gianni is an expert in autonomous systems. Basically, he works in this area, autonomous intelligent systems. His work is strongly focused on building robots to do search and rescue missions. This could be after an earthquake, or when a building's fallen down, there's a little hole left open. In goes a little autonomous or partially autonomous robot to have a look round where you can't get a person. He's also interested in using this technology to go to places that humans can't go, like in nuclear power stations, where the radiation levels make it impossible for people to go in there. He's also interested in renewable energy as well. So you can imagine you can have drones, or you can have robots which can go and service things offshore, which is a very useful thing to do, where it's difficult to get people to get to. He's also interested in other applications of robotics, and recently he's started doing this sort of creative digital robotic project, getting robots to act a little bit like artists. And you can see here on this particular drawing here, he's got the robot to actually draw stuff out as if it was a professional sketcher, whatever you call them. So we got another lecturer, Sven Gaudel, who is interested in interactive systems and social robotics. So he's very much interested in building low-cost systems, but can also act with a sort of a social companionship role. And he's come up with a couple of designs. And the idea is it's sort of mimicking a kind of an animal, which is a soothing thing to be around. He's also interested in electronic health projects as well. How can we monitor people to make sure everything's okay? Dr. Martin Stollen is based basically. It works basically with soft robotics. So these are machines which, unlike big powerful machines like the standard kind of robots that we have, they're sort of more inspired by human movement and how the human arm and body operates. So we are quite safe things to be around, people, not karate experts, but generally speaking, you don't use much force when you're actually moving your arms. You just use what you need. And we're quite soft. We could bang into the wall and it's not going to knock the wall down. That's not the case with a big industrial robot. It would knock the wall down. So Martin's very much interested in how can we build robotic arms which are very soft. They run through springs, if you like, making them very safe to be around. And he's been applying this technology to agriculture. So one really good project at the moment is actually building this robotic arm, the gummi arm he calls it, because gummi is Norwegian for rubber. So it's a soft arm that he's now using to pick raspberries autonomously. Another lecturer, Dr. Chin-Zu Lee, specialises in machine learning and AI for robotic applications, and he's interested in, first of all, machine vision, and in fact he teaches a lot of the vision at the university. But he's also interested in robot interaction, so some of the projects he's been working on, for example, are using systems to sort of basically record the intent that you want to do with the robot using things like Connect and this kind of things, and then controlling remotely systems to actually do something, such as this Baxter robot down here. He's also interested in looking at issues of control and issues of kinematic analysis. So that really sums up my very brief discussion of robotics in Plymouth. Hope that's given you a bit more of an idea of what we actually do here. Of course, if you've got any questions, you can always email the admissions team, admissions@plymouth.ac.uk, and they'll certainly pass on your information to us. Thank you for your time.